Good afternoon, everyone. Those of you who are listening in. Today we are doing the chapter on the sources of magnetic fields. Okay, now I'm starting at question number 9. Ronald should have covered question 1 to 8. I'm doing question from 9 to 16, and it's all having to do with the sources of magnetic fields. You have studied magnetic fields up to this point. Now we're just doing the sources of magnetic fields. So, number 9. The question reads as follows. Okay, let me just get that in front of me. In the figure, what is the magnitude of the magnetic field at point P? So we want the magnitude. So we want the magnetic field at point P. What is the magnitude of the magnetic field B at point P? Okay. Express your answer in terms of mu naught, the permeability of free space, the radius A, and B, and the current I. So we have this funny shape here. Okay. The bigger circle has a radius of B, while the smaller circle has a radius of A. So the bigger circle has radius B, the smaller circle has a radius A, and the smaller circle is 1/4 of that circle, while the bigger circle is 3/4 of the circle. Okay, so first of all, how do we calculate the magnetic field at the center of a circle? How do we calculate the magnetic field at the center of a circle? This is how we do it. Magnetic field at the center of a circle is equal to, and this is the easy formula derived from the Biot-Savart law. It's mu naught times the current, so the permeability of free space times the current, divided by 2 times the radius. Okay, this is how you calculate the magnetic field at the center of a circle. Okay, this is the formula for B at the center of a circle. Center of a circle. So B at the center of a circle. And my apologies, this thing just keep getting notifications that I'm writing on. Okay, so first of all, let's calculate the magnetic field at point P due to circle of radius A, the smaller circle. Okay, so the magnetic field at the center of the circle due to the circle, the quarter circle of A. Now remember, it is a quarter circle. Okay, with radius A. It's just 1/4 of a circle. So let's calculate first of all, what's the general formula? Mu naught I. I think I should put the, I don't know what notifications are coming in here. Let me just put, uh, it's just updating here. Okay, so mu naught multiplied by the current divided by 2 times the radius. And in this case, the radius is A. Okay, but remember, this is not a full circle, it is only a quarter of a circle. It's only a quarter of a circle. Okay, so therefore the magnetic field due to that quarter of a circle of radius A is equal to mu naught times the current divided by, and then 8A. Okay, that is the magnetic field due to the quarter of that circle. Okay, now of course you can then use the right hand rule to see that the circle in this case, it's pointing in that direction, so the magnetic field is going into the page at point P. It's going into the page according to the right hand rule. Now the magnetic field due to the circle of radius b is equal to, we use the same formula, mu naught times I over 2r. In this case, it's mu naught times the current is still I. The current does not change, but the radius of the circle is now no longer A, it is now B. So 2B, but, and in this case, it covers the rest of that circle of 3/4. Okay, and that gives us an answer of, if you multiply that all out, it's 3 mu naught I, and it's also going into the page, times 8b, right? Times 8b. So that is the magnetic field due to both of those sections of the circle. Okay, so what is the combined magnetic field strength at point P then? It'll just be the sum of these two. So this one plus that one. In this case, we can see it is 3 of mu naught I plus 8b. Okay, you'll see now. So B net, so the net effect or the net magnetic field at that point is equal to mu naught I over 8a plus 3 mu naught I plus 8b, and if you add them up, or you can take out the common factor of mu naught I over 8, that's 1 over a left over plus 1 over b left over on that side. Now if you were to do your basic math, adding of fractions, you will get the common factor for these two is AB, and on this side you will have B plus A. Okay, so the answer should be mu naught times I over 8 B plus A. Let's go check into that options if there is one that says mu naught I over 8 B plus A or A plus B AB. Here's one that's, but it's over 4 mu naught 8 3B. No, can't be this one because it's over 4. Here's mu naught I over 8 B plus 2A. Oh, I think I forget here. It's 3A here. Sorry, 3A. Should be 3 there. Forgot that it's 3/4, remember? So it's 3A. Mu naught I over 8B plus 3A over AB. So that's the correct answer, E. Let's check. E. Yes, it is indeed the correct answer. Okay, I just want to check something. You are going to have to learn to be comfortable or try and get comfortable with using only uh, figures or symbols at this point, because it's very rare that you're going to have to deal with actual numerical numbers. Okay, so question number 10. Here we have this 3/4 of a circle. Okay, with the smaller part being having radius A and the larger part having radius B. Okay, again, what is the magnitude of the magnetic field at point A or point P? If A is equal to R and B is equal to 2R. Okay, so the radius of B is double that of A. So what is that magnitude? Let's see. Now, the magnetic field due to point A is just similar as to what we did before. Remember, we have mu naught times the current over 2 times the radius of that circle, which in this case is A. Okay, in this case the radius is A, and it is 3/4 of a circle, so it's 3 times 4. So if we were to write it out, let me rather just write it right next to it so I can have some space. So it's I mu naught I over 2a times 3. That's times 3. So there's a 3 on top. 3, 3 on top. And then 4 at the bottom. 4 times 2 is 8a. So 3 over 3 mu naught I 8a. Okay. Now that is just 3 mu naught I 8r. Why do I write r? Because a is equal to r. Okay. So the magnetic field due to the 3/4 circle of radius b can then be written as mu naught I. By the way, this one is going into the page. It's into the page at point P, into the page at point P, and you can check that using the right hand rule. Okay, it's sorry, no, I'm checking now, and it's going at point P. It's coming out of the page, out of the page. Sorry, that's out of the page, out of the page. Just hold your right hand right there, curl it in the direction of the wire, and your thumb will point in the direction of the magnetic field. Or curl your finger in the direction of the magnetic field, and you'll see that it is curling in that direction, and it will all come out at point A, or rather point P. So mu naught, so that's out of the page, mu naught over 2A, still the same general formula. But in this case, it should be 2R. What is the radius in this case? It's not A, it is B. Okay, so, and that is also 3/4 of a circle. So it is 3 mu naught I over, it's 4 times 2, that's 8, times B is equal to 2R. So it is 8 times 2, which is 16R. That's 16R. And that's into the page. It's into the page. You can check it there. Into the page at point P. Okay. Now, this one is bigger. Okay. The one BA, due to the smaller 3/4 circle, is bigger. Okay. Now B net. Remember, one is pointing in and one is pointing out. The electric field coming out is bigger. So I'll just write there BA is bigger than B magnetic field due to B. So B net is equal to the magnetic field at point A minus the magnetic field at point B, which is equal to 3 mu naught. I'm just going to sum them. 3, 3, 16R. The common factors is 3 mu naught R. Or let me just rather do it the old-fashioned way then, and write the whole thing out. 3 mu naught I over 8R. Let me see if it's still fitting on the page. Minus 3 mu naught I over 16R. The common factor here is 16 and R. We double this one, so it's 6 mu naught I minus 3 mu naught I. So that leaves you 6 mu naught I minus 3 mu naught I is this 3 mu naught I over 16R. So 3 mu naught I, 3 mu naught I over 16R is the answer that we got. And let's go check if there is a 3 mu naught I over 16R as an answer. 3 mu naught I 4R. No. 3 mu naught I 16R. And let's check 3 mu naught R over 16R. Your answer is correct. It is 3 mu naught R, 3 mu naught I, oh, over 16R. Okay, that is wonderful. Question number 11. Question 11. The figure shows a cross section of three parallel wires, each carrying a current of I. Okay, so there's three wires there. They each have a current of I. The currents in wires B and C are out of the page, so B and C are out of the page in the positive z-axis, while the wire A is into the page, into the negative z-axis. Okay, so the distance between each wire is indicated as 2r and r. What is the magnitude of the force per unit length on wire B? Okay, express your answer in terms of mu naught, r, and I. Okay, now, first of all, the force per unit length due to two different current carrying wires that are parallel can be calculated as follows. The force per unit length, so force per unit length is equal to mu naught times the current in 1 times the current in 2 divided by 2 pi times the distance between those two wires. That's how you calculate the force between two wires that are parallel. Okay. Now, if the currents are flowing in the same direction, it is repulsive. If it's flowing in the opposite directions, it is attractive. Okay, so if currents are flowing in the same direction, the wires will repel each other due to Lorentz force, no, the magnetic force of repulsion, and then they will attract if the wires are flowing in opposite directions. But remember, the currents, if the currents are flowing opposite direction, but the wires are still parallel. Okay, so the force between B and C therefore will be repulsive. So the force between, while the force between A and B will be attractive. Okay, so C will push B towards A and A will attract B towards A. So both of these forces will have a net effect of pushing it towards A, pushing B towards A. Okay, so by the way, therefore, if you rewrite this as the force is just equal to mu naught I1 I2 times L over 2 pi the distance. Okay, so let's first calculate the force between B and C. The force between B and C. Force between B and C is mu naught. It's just a constant. The current 1, both of their currents are I, so we can just write I squared times the length, because it's force per unit length, but I just multiply on both sides by L. And then 2 pi times the distance between B and C. In this case is R, 2 pi R. Okay? So that's the force. And these two is, like I said earlier, it's repulsive. So it's repulsive. In other words, it is towards the left. It's towards the left. The negative x-axis, if you will. In this case, it's towards the left. Now the force between A and B, remember we want the net force on B. So the force between A and B is still mu naught. Then we have the currents are all I, so it's still I squared. The length is there, 2 pi. Basically, the only thing that's changing is the distance between them. 2 pi times the distance between these two, B and A, is R, 2R. Okay, therefore, the force therefore is mu naught I squared L over 4 pi. Should be then 4 pi R. Now, since both of these forces are in the same direction, we can just add them up. Okay, so the net force, F net, is then just equal to F BC plus F AB, and that's equal to, it's 4 pi R, that's 2 pi R, The common factor 4 pi r is 4 pi r, so that's 2, so it's 3. If you add those two up, it's 3 mu naught I squared over times L over 4 pi r. The common factor, I'm not going to go through the whole thing because you should know how to add fractions, but the common factor here, 4 pi r and 2 pi r is 4 pi r, and then you multiply this one by 2. Okay, you can write it as this. This is exactly the same, so I'm going to write 2 here, multiplied by 2, and multiply the bottom part by 2 as well. So it will be 2 pi, 2 mu naught I squared L over 4 pi r. So the common factor is now 4 pi r both. So that will stay 4 pi r. So that's mu naught I squared L, and that's 2 mu naught I squared L. So it will be 3 mu naught I squared L. Okay, simple beauty of math. So it will be 3 over 3 quarters mu naught I squared 4 pi r. By the way, we are calculating not the force, but the force per unit length. So if we divide both sides by L, if we divide both sides by L, we have the force per unit length. And this is the answer. We settled 3 mu naught I squared 4 pi r. Let's check. Your answer is correct. 3 mu naught I squared 4 pi r. And that is wonderful. Okay. Question number 12. Question 12. The figure shows a cross section. Now we've done with parallel wires. We've done this formula that deals with calculating the force between two parallel wires. Now in this case we have three parallel wires. Okay, but they are set in the shape of a triangle. Okay, so and they each have a current of I. Now the currents in wire A and B. So in A and B it's into the currents in A and B are out of the page, while that in wire C is into the paper. Okay, now what is the magnitude of force per unit length on wire A? So it's exactly the same as the previous one. What is the formula for force per unit length? It is mu naught times the current I, 1 times the current in the second one, divided by 2 times pi times the distance between them. Okay, now in this case, the force between A and B, let me just place the drawing there. The force between A and B is just mu naught. Remember, both of them have a current. A and B has current I, so it's I squared is the current. I times L. Remember, L is here at the bottom, so we just multiply both sides by L, the length. So we can just get the force. 2 pi, we're just going to divide at the end again by L, so that is just unnecessary. We can leave it there. Okay, so 2 pi, just a mathematical trick. So, and the distance between A and B is R. So that's the force, mu naught 2 pi R, between A and B. Now let's calculate the force between, and by the way, we need to calculate what is the force. In this case, it is two. They're in the same direction out of the page, so they will be repulsive. 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 So this force, in this case, let's assume this is point P. This is point P. Oh, sorry, not P. A. We want the force on A. So this force due to B will push this in that direction. Okay, it's repulsive straight along that line. However, the force due to C, force AC, this force, however, is attractive because they are in opposite directions. They're parallel, but the currents are flowing in opposite directions. So, if we were to work it out, the force will still be mu naught. The currents, both of them have I currents. L is there. What is the distance between them? It's 2 pi. And the distance between them is R as well because it's a isosceles triangle. Or equilateral. Equilateral, I think. Okay, so now this force, force AC, this is force AB, FAB. This is force AC because it's attractive. So this is force AC. Okay, so that's force AC, that direction. Okay, both of them have horizontal and vertical components, but the vertical components will cancel out because they will be exactly the same and in the opposite directions, and they will cancel. So the only force then would be the net force. Okay, the net force. The net force will be both of their horizontal components. Okay, so it'll F net will be equal to the horizontal component of AC, AC, and the cosine. Remember, this is 60 here. This angle is 60. That angle there is 60. Basic congruence, your basic geometry. Those angles will be 60. So it will be the cosine of 60 degrees. The force of AC times the cosine of 60 plus the force of AB times the cosine of 60 degrees. Now, what do we know about the cosine of 60? Well, that is how you calculate the horizontal components. Okay. Now, uh, the force of AB and the force of AC. What do we see here about AB and AC? They are exactly the same. These forces are the same. Okay. These forces are exactly the same. So, it'll just be twice one of them. Okay. So, it'll just be 2 times, say, AB, which is mu naught I naught L over 2 pi R, and then cosine of 60. But there's a 2 there and there's a 2 there at the bottom. So finally, and then we need to divide both sides by L because we want to per unit length. So it's just mu naught times I squared. This will be F net per unit length, mu naught I squared over pi R. That is what you should get. Okay, times cosine 60, of course. Cosine 60. I almost forgot to include that. So let's check if there is an answer that provides us an option that provides us with that answer. So cosine 60 mu naught I squared by R. And let's check. Your answer is correct. Okay. So we have done that mathematics correctly. Okay, question number 13. As shown in that figure. Okay. This is a nice question. I like it. As shown in that figure, the current in the long straight wire I1 is 5 amperes and the wire lies in the plane of the rectangular loop which carries a current I2 of 10 amperes. Excuse me. A is a distance of 0.5 meters. The dimensions in the figure are as follows. C is zero point 0.1 meter, A is 0.15 meters, and L is 0.45 meters. What is the magnitude and direction of the net force exerted on the loop by the magnetic field created by the wire? Okay, so this wire is going to create a magnetic field around it. And what will be the direction of that net magnetic force? Okay, so now to the right of that long straight wire, this one I1, carrying current 1, it's going to create a magnetic field that's going to be circular around the page. It's going to come out on the left hand side of that long wire and go into it on the right hand side of that wire. Now, by symmetry, we see that on the top part of this rectangle and on the bottom part of this rectangle, the magnetic forces are going to cancel. Okay, they are going to cancel out. So we are only concerned with the magnetic force on the vertical segment. Okay. So the net force on those vertical segments. This is question number what? Question 13. So the net force on those vertical segments, okay? So it's only these two that are parallel, okay? The one at a distance c away and the one at a distance c plus a away, okay? The horizontal components of the rectangle, uh, those forces will cancel out due to symmetry arguments, okay? So the net force on that rectangle will be the force on arm number 1 plus the force on arm number 2. Okay, so the force on arm number 1 is going to be mu naught times the current in 1 I1 times I2 times the length of that line, which is L in this case, 2 pi times the distance it's away, in this case it's C, 2 pi C, plus plus I'm checking something here, magnetic field, right hand rule, up, push it in here, okay. Okay, we're going to determine directions now. And then for the second one, it's also mu naught, still I1, the current in that part. To remember, we're looking at the two horizontal components of the rectangle now, these two. Okay, in this case, the current is going to be flowing up, and in this one, it's going to flowing down. Okay, we cancel on the bottom and the top, the electric field force is going to be zero. Or by symmetry, it should be canceling out. Okay, so the magnetic field at these points, that will be 2 pi, and the distance is, what distance is it away? It's C plus A, C plus A, okay, and of course the length L. Now let's look at the directions. Okay, what directions will the force be in this case? Okay, will it be into the page? But it can't be both in that case. Okay, in one case it's going to be into and one out. Okay, and we want the magnetic field due to the, we want the magnetic force due to that one created by I1. Okay, now if we were to say at this point, okay, remember these magnetic fields will be in opposite directions at these 2 points or along these two lines. Okay, it will be repulsive in at this point here. Okay, it will be repulsive. The magnetic force will be repulsive. The force will be repulsive. So let's say at that point, let's make it a negative. Okay, let's make this negative. It will be repulsive, and at this point it will be attractive. Okay, because it's going to be flowing, the current's going to be flowing in the opposite direction, it's going to be flowing down on the second part of the rectangle. Okay? So if you were to take out the common factors, mu naught I1, I2, L over 2 pi, you are left with negative 1 over C plus 1 over C plus A. Okay, that is what you should be left with. Okay, due to the one force being repulsive and the other one being attractive, or the forces, the two different forces due to the different directions the current is flowing. Okay, now if you were to plug in all values, but let's just simplify it a bit now. U naught, I1, I2, L. If you simplify this, you will be left with C times C plus A. That's the common factor over negative A. That will be your value. Now, if you plug in all values, okay, if you were to plug in every single one of those values, where mu naught is 4 pi times 10 to the negative 7, I1 is equal to, here it says there, 5 amperes. If you plug in I1 as 5 amperes, oh, by the way, I left 2 pi out. I2 is 10 amperes. L, the length, is 0.45 meters. 2 pi times negative A, the length is 0.15 meters. C is what is C? 0.1 meters. If you plug in all of those values, okay, we don't have any space there, but if you were to plug them all in, you will get negative 27 newtons. Let me just check here. It's micro or milli? Just gonna check. It's micro, yeah. Micronewtons. Negative 27 micronewtons. Okay. Micronewtons. Negative 27. That means along the negative x direction. So along the negative x direction. So along the negative x direction, negative 27 micronewtons. The negative x-axis. So check. And the answer is correct. Okay, wonderful. Okay, question number 14. This is an easy one. Gauss's law states that the net electric flux E integral, the closed integral of the electric field through a surface area of any closed surface is proportional to the change to the charge enclosed. Okay, this is Gauss's law, and it came in very helpful in electric fields. Now, the analogous formula for magnetic fields is, what is the analogous for magnetic fields? Now, the one for magnetic fields is the following. For magnetic fields, that the magnetic field through any closed surface is equal to 0. Yeah, that you should know. It's just a theory question. Yeah, that's correct. 15, second to last question. Remember here, the magnetic field through any closed surface is equal to 0. That's Gauss's law. That is analogous to that one. Okay, now 15. A long cylindrical wire of radius 2 centimeter carries a current of 40 amperes. Okay, that is uniformly distributed over the cross section of the wire. What is the magnitude of the magnetic field at a point which is 1.5 centimeters from the axis of the wire? Okay, so we have that the radius of the wire is 2 centimeters, or 0.02 meters. Let me write it down. Radius is 0.02 meters. The current carried by the wire is 40 amperes, uh, and the distance from the axis where you want it to calculate the magnetic field is 1.5 or 0.015 uh, 0.015 meters. Okay, and of course the permeability of free space is 4 pi times 10 to the negative 7 Tesla meter amperes. Okay, now how do we calculate all of this? Okay, first of all, we need to calculate the current enclosed by that uh, radius 1.5. So the current enclosed is equal to the total current multiplied by the radius at which you want the smaller section of the pipe or the current divided by the total radius. Okay, so that is equal to, it's 40 amperes multiplied by, that is small r 0.015, which is the radius, a section 1.5 centimeters from the axis, and it's squared. Don't forget to square, and then the total radius is 0.2 meters, and you square that as well. And then you will have the enclosed current is 22.5 amperes. So the current enclosed at a distance of 1.5 centimeter is 22.5 amperes. So now we have the current enclosed. Okay? Therefore, we then apply Ampere's law. Guys can still remember Ampere's law. Magnetic field enclosed, dl is equal to, in a certain length, is equal to mu naught times the current enclosed. We already calculated the current enclosed. We have mu naught, and we want this is for a circular loop. Okay, so the magnetic field is uniform, so it is dl. It's a circular loop. Mu naught enclosed. Now the the this is basically the circumference of a circle, which we can write as 2 pi r. Mu naught I enclosed. This only works for a circular value. So mu naught times I enclosed. I could have just written this formula at the end here, but I rather wanted to show you how we got it. You should actually know it by now. 2 pi r. Okay. Now if we plug in what we know, all the values we have, 4 pi times 10 to the negative 7 as mu naught. The current enclosed 22.5 amperes. Also, this should not be big R. This should be small r. This should be small r. So that's not big R. 2 pi times small r, which is this case is, or is it big R? Let me check. It's the circumference of the whole circle, right? Yes. No, it's still small r. So this will be small r 0.015 squared. No, not squared in this case. And therefore, if you were to work this out, or rather you should then get r squared, so it's r should be on top, this will only be r, and on the bottom there should be r squared. Okay, so If you were to calculate all of that out, you should get 3 times 10 to the negative 4 Tesla. Okay, so 3 times 10 to the negative 4 Tesla. So that is what the magnetic field is at a distance of 3. So this is how you calculate the magnetic field. The magnetic field at a certain distance in a current carrying wire is equal to this formula here. Let me just highlight it rather. This formula, you use this formula. It's a very important formula. Mu naught, the magnetic field is equal to mu naught times the current enclosed in that section of wire, 2 pi times the radius of that small section. Okay, in this case 3 times 10 to the negative 4 Tesla, or zero point 0.3 millitesla. 0.3 millitesla, let's check. Your answer is correct. It is indeed 0.3 millitesla. Last question in this case. Question number 16. A long wire is known to have a radius greater than 4 millimeters and to carry a current uniformly distributed over its cross section. Okay. If the magnitude of the magnetic field is 0.2 millitesla at a zero point 0.4 millimeters from the axis of the wire and 0.2 millitesla at a zero point 0.10 millimeters from the axis, is what is the radius of the wire? Okay, so we want the radius of the wire. Now, this formula here can also be written in this way. Mu naught, instead of writing the enclosed current, we write mu naught times the current that's been given times the small radius inside divided by 2 pi times the radius r of this thing, r squared. It's the exact same formula. Now, let's use this formula. Okay, this is for 16. The magnetic field at a point, it has a radius greater than 4 millimeter. Okay, magnitude of the field is at 4 millimeters, and at zero point 0.2 millimeters, it's at 10 millimeters. It has a this magnetic field. So they give us the magnetic field at 10 millimeters, and they give us the magnetic field at 4 millimeters. Okay, from the axis. Okay, so they ask us to calculate what's the radius of this wire. So they want us to calculate big R. Okay, so the formula we need is this one: mu naught I, this is small r, over 2 pi r squared, where r, this big R is the radius of this wire. This is what we want, big R. And this small r here is the distance from the axis. Small r is the distance from the axis. Big R is the radius. Okay. Now, for a point inside the wire, it's 4 millimeters. Remember, they say it has a radius greater than 4 millimeters. So, if where r, for inside, where r is equal to 4 millimeters, it's inside. So B at r equals to 4 meters, it's inside the wire because they tell us it's greater. So B inside is equal to B1 or B inside. Let's just write it like this. It's mu naught times the current of in this wire times the distance that it is inside. So this in case it is 4 millimeters in this case, and it is 2 pi r1 equals 4 millimeters, and we want r. Okay, so the outside the wire, be outside the wire, where R is equal to 10, R2 is equal to 10 millimeters, we have mu naught I R2 2 pi over R. This R squared value here, big R, capital R, should be exactly the same for both of them. Okay, now from the equation of the magnetic field, okay, outside the wire, this equation, we can calculate the current as, so I, therefore, we can say that I, if we make I the subject of the formula, the current is equal to 2 pi R squared, 2 pi R squared divided by mu naught. R squared B2 mu naught. Okay, or rather, this is not big R here, this is just small r because it's outside, so it's small r, R2. This is just the formula for the magnetic field outside the wire, so let me just check that. For the magnetic field inside, we use this formula for inside, but for a magnetic field outside of a wire, the magnetic field is just, for magnetic field outside a wire, the magnetic field is mu naught I, 2 pi, and then the distance it is outside the wire. I forgot that part, it's a formula. Don't switch those two up. This is just for inside a wire, and this is for outside a current carrying wire. Now, if you make I the subject of the formula, I was wondering how I got that. So anyway, it is then 2 pi r squared times the magnetic field outside, over mu naught. That's the current. Okay. So now you have a formula for the current. Now, if you substitute this formula into, or rather, if you substitute this formula for the current into this formula here, B, okay, for the magnetic field inside, you get the following. For the magnetic field inside, if you substitute that formula for current, you get the following. Mu naught, still there. That the new formula for current is the one that we just determined, 2 pi r squared. What do we have there? The magnetic field outside over, what is that? Over mu naught, of course. Outside over mu naught. What was still on top there? It's mu naught. The current there was R1 is over what is still on the bottom here, 2 pi r squared. You can just go back or pause there, see if you can do it yourself. Just substitute that in there, and if you simplify it, it just means B magnetic field on the inside is equal to, that cancels, that cancels, 2 pi cancels there, r squared. So basically what is left is the radius R2, B outside, R1, the radius inside, and then R squared, which is what we want. Now we want R squared, so we'll rearrange the formula. The get r squared. So it's just the magnetic field in the radius of the inside, radius outside, times the magnetic field outside gives you divided by the magnetic field inside. So if you plug in all of the formulas, all of the players, okay, the radius inside is 4 millimeters. So it's 4 times 10 to the negative 3. Outside is 10 millimeters. 10 times 10 to the negative 3. The magnetic field outside is zero point 0.2 millitesla, zero point 0.2 times 10 to the negative 3. And the magnetic field inside is 0.285 millitesla. And all of that, if you therefore then work out R, you'll find that R is approximately 5.3 millimeters. So the radius of this wires are 5.3 millimeters. So 4 is inside and 10 is outside. So 5.3 millimeters. Let's check. And that is indeed correct. Okay, thank you for watching, ladies and gentlemen. I hope you have understood. And you should just go back if you don't understand anything. But I'm going to stop here and wish you all the best. Hope you understand. Thank you for listening.